It is June 19th, 1944. We are in the heart of Normandy, France. On the side of a dusty, narrow dirt road near the village of Villers-Bocage, a massive German Panther tank sits idle. Its engine is idling, a low, rhythmic rumble vibrating through the steel hull. There is no smoke rising from the hatch, no signs of a struggle, and no shells have impacted its thick armor. There are no Allied P-47 Thunderbolts circling in the sky, and no British Fireflies are hiding in the tree line. To a casual observer, the tank looks ready for battle, but the crew inside knows the truth. They have been sitting in this exact spot for 6 hours, and they aren't going anywhere. This 200,000-pound masterpiece of engineering, which cost the German state 450,000 Reichsmarks and 6 months of specialized labor, has been reduced to a very expensive, very heavy roadblock. The Panther didn't lose a duel. It didn't get outmaneuvered. It simply tried to turn. When the driver engaged the steering lever, the final drive, the mechanical heart that transfers power to the tracks, simply gave up. An internal gear shattered, and the tank became a monument to a single engineering oversight. This was not an isolated incident. This was the silent epidemic that hollowed out the German armored divisions in the West. By the end of the Normandy campaign, the statistics told a shocking story. More than 80% of Panther losses were not caused by Allied anti-tank guns, airstrikes, or artillery. They weren't even caused by the legendary 17-pounders of the British tanks. They were caused by a mechanical component that was undersized by exactly 10 millimeters. To understand how the pride of the Panzerwaffe became its own worst enemy, we have to look back to the summer of 1943. Germany had just unveiled the Panzer V, better known as the Panther. On paper, this vehicle was a nightmare for any Allied commander. It was the definitive answer to the numerical superiority of the Soviet T-34 and the American Sherman. The Panther's 75mm KWK-42L/70 cannon was a marvel of ballistics. It could penetrate 140 millimeters of vertical armor from a kilometer away. At that range, it could destroy a Sherman tank from any angle. It could knock out a T-34/85 frontally before the Soviet crew even saw the muzzle flash. It was a weapon of absolute precision and terrifying power. The armor was equally impressive. The frontal hull was protected by 80 millimeters of steel, sloped at a 55-degree angle. In terms of physics, that slope made the armor behave like 140 millimeters of vertical plate. In 1944, no standard Allied anti-tank weapon could penetrate that front plate at practical combat ranges. It was effectively invincible from the front. German technical assessments were glowing. They believed the Panther was qualitatively superior to anything the Allies had in France, and even superior to almost everything on the Eastern Front. On the battlefield, the theory seemed to hold up. In isolated engagements, Panther crews were racking up kill ratios of 5-to-1, sometimes 8-to-1. A single Panther, tucked into a well-chosen defensive position, could hold a vital road junction against an entire Allied armored company for hours. This was the lesson the British learned the hard way at Villers-Bocage. In just 2 hours, a handful of German heavy tanks paralyzed an entire advance. This led German high command to a logical but ultimately fatal conclusion. Quality would always compensate for quantity. They believed one Panther was worth 3 Shermans. That became the core of their operational strategy for the defense of France. But that strategy was built on a foundation of sand. The tank was failing under its own weight, and the cause was hidden deep inside the lower hull, tucked behind the drive sprockets. It was the Seitenvorgelege, the final drive. In any tracked vehicle, the engine creates the power and the transmission manages the gears. but you cannot connect a transmission directly to the tracks. The torque required to move 45 tons of steel is so immense that it would snap a standard drive shaft like a toothpick. You need a final reduction stage, a set of planetary gears that multiply the torque one last time before it hits the sprocket. Think of it like a mountain bike. When you hit a steep incline, you shift into the lowest gear. Your legs spin very fast, but the bike moves slowly. You are trading speed for the raw force needed to climb. A tank's final drive does this on a massive scale. It takes high-speed rotation from the engine and converts it into low-speed, high-torque power to churn the tracks through mud and over obstacles. The pressure on every gear tooth in that final stage is almost impossible to imagine. We aren't talking about pounds of pressure. We are talking about metric tons of force applied to a tiny surface area every single time the tank moves. If those gears aren't designed to handle that specific load, the metal will eventually scream, then crack, then shatter. Here is where the engineering disaster began. The Panther's final drive was never designed for a 45-ton tank. When the project started in 1941, the requirements called for a vehicle in the 30 to 35-ton range. The engineers at MAN, Maschinenfabrik Augsburg-Nürnberg, built a final drive that was perfectly adequate for that weight class. But as the war progressed, the design grew. Hitler and the German High Command demanded more armor. They wanted a bigger gun. They wanted more equipment. By the time the Panther hit the production line in early 1943, it had ballooned to nearly 45 tons. But in the rush to get the tank to the front, the final drive housing and its internal gears were never fundamentally redesigned to account for that 28% increase in mass. The engineers knew there was a problem. In April 1943, Heinz Guderian, the Inspector General of Armored Troops, received a technical report warning that the final drive showed accelerated wear under high torque. The recommendation was simple: redesign the housing and increase the face width of the gears. But the political clock was ticking. Hitler wanted the Panthers ready for the massive offensive at Kursk. The redesign was shelved. To understand why 10 millimeters of metal mattered so much, we have to look at a concept called Hertzian contact stress. Imagine two curved gear teeth pressing against each other. They don't touch over a wide, flat area. They touch along a tiny, microscopic sliver of metal. All the weight and torque of the tank are concentrated on that tiny ellipse. Think of a ballpoint pen. If you press the tip against your hand, it's uncomfortable but manageable. Now, take that same force and apply it to a needle. The needle has a much smaller contact area, so the pressure per square millimeter skyrockets. The needle breaks the skin. That is exactly what was happening inside the Panther's gears. Because the gears were too narrow, the pressure exceeded the endurance limit of the steel. Below this limit, steel can be stressed millions of times without failing. But once you cross that line, microscopic cracks begin to form beneath the surface of the metal. You can't see them. The driver can't feel them. The tank feels perfectly fine, until it doesn't. Every time a Panther driver in Normandy made a sharp turn, those cracks grew. Eventually, a chunk of the gear tooth would break off in a process called spalling. That metal fragment would then be swept into the rest of the gears, acting like a grenade. Within minutes, the entire assembly would seize, and the 45-ton beast would become a stationary target. Engineering calculations for a 45-ton tank required a gear face width of at least 65 millimeters to keep the stress below the failure point. The Panther was produced with a face width of only 55 millimeters. That missing 10 millimeters of steel was the difference between a functional weapon and a mechanical liability. The geography of Normandy made this flaw catastrophic. The Bocage country is a labyrinth of ancient hedgerows and earthen embankments. The roads are narrow and the fields are small. Maneuvering a tank in this environment is a nightmare. It requires constant, sharp, low-speed turns, the exact type of driving that puts the maximum possible torque on the final drive. In the wide-open plains of Russia, a Panther could drive in a straight line for miles, allowing the gears to operate under steady, manageable loads. But in the hedgerows of France, every 100 yards required a pivot or a sharp correction. Every turn was a hammer blow to a gear that was already operating past its breaking point. The data from the campaign is brutal. The mean distance between failures for a Panther's final drive in Normandy was only 150 kilometers. That's less than 100 miles. A modern car covers that distance on a grocery run. An American Sherman tank could cover 10 times that distance with nothing more than routine maintenance. When a Panther broke down, it wasn't a quick fix. In the field, without a specialized heavy recovery crane, it could take a crew 12 to 16 hours to replace a final drive, if they even had the spare parts. In the fast-moving mobile warfare of 1944, 16 hours was an eternity. Most of the time, the front line would shift, and the crew would be forced to blow up their own multi-million-dollar tank to prevent it from falling into Allied hands. The story of Panzer Lehr, one of Germany's elite divisions, illustrates the scale of the disaster. They entered the fight in June with 89 operational Panthers. These were the best crews, led by the best instructors. By late July, they had only 14 tanks left. Of the 75 they lost, the vast majority were not destroyed by the Allies. They were listed in German logs as mechanical breakdowns. While Germany struggled to keep its few Panthers running, the Allied industrial machine was operating on a different scale. American factories were churning out 400 Shermans a month. The British could replace every single tank lost in Normandy within 60 days. The Allies didn't need their tanks to be better, they just needed them to show up. The Panther was a masterpiece of tactical design, but a failure of operational reality. It proved that a weapon system is only as good as its weakest link. In this case, the link was a gear that was just a little too thin. The bravery of the German tankers couldn't fix a math error made in a factory hundreds of miles away. Heinz Guderian later wrote that a weapon that cannot reach the battle is no weapon at all. He wasn't talking about the gun's range or the armor's thickness. He was talking about the logistical heartbeat of a mechanical army. He was talking about the 10 millimeters of metal that effectively lost the armored war in the West. The story of the Panther in Normandy is a reminder that in war, the loudest explosions aren't always the ones that decide the outcome. Sometimes, it's the silent cracking of a gear deep inside a machine that changes the course of history. It wasn't just Allied firepower that cleared the road to Paris. It was the weight of a tank that its own legs simply couldn't carry. If this look into the hidden engineering of World War II changed how you see these legendary machines, there is much more to uncover. The decisions made on the factory floor often outweighed the decisions made on the battlefield. To see the technical side of history that rarely makes it into the textbooks, make sure to stay tuned. The next story is just as specific, just as technical, and just as vital to understanding how the world was won.